But these exact same materials have a hidden vulnerability. If you push on them instead of pulling, applying longitudinal compression, their structural strength drops by up to 40%. To compensate for this structural weakness, aerospace engineers have to over-engineer aircraft components, packing on excess weight to guarantee safety under compressive loads. That sudden, catastrophic loss of strength comes down to a highly specific physical reaction known as fiber kinking. To understand how a solid aerospace panel snaps under pressure, we must scale all the way down and watch the physical geometry of a micro-collapse. Down at the microscopic level, these materials look different than the pure math suggests. Rather than sitting in perfectly straight, uniform rows, the individual fibers naturally have slight waves and misalignments locked inside the surrounding polymer matrix. When longitudinal compression pushes down on the ends of the material, that pressure forces those microscopic bends to curve even further. Because the fibers are already resting at slight angles, the downward push translates into lateral movement. The rigid fibers start pressing sideways against the surrounding epoxy resin. This sideways push creates what engineers call shear stress. The epoxy matrix is suddenly under immense pressure as it fights to keep those bending fibers locked in their original straight alignment. This microscopic image shows exactly where that fight is lost. Tiny, naturally occurring empty pockets in the matrix, called microvoids, act as stress concentrators. The matrix loses its grip around these voids first, initiating early microcracks. As the shear stress overwhelms the matrix's yield strength, the polymer permanently deforms. Those tiny cracks merge into much larger cavities, completely stripping the fibers of their lateral support. Without the matrix holding them straight, clusters of unsupported fibers begin to tilt cooperatively. They form a shallow angle known as a microbuckle band. The material has officially reached its point of no return. At this exact threshold, the internal physical balance collapses. The matrix can no longer sustain equilibrium against the incoming force. This chart shows the material's structural limit. Notice how the steady upward climb suddenly curls sharply backward and downward. This charts the snapback instability, a highly nonlinear state where the structural load drops to near zero in an instant and the fibers rapidly rotate. Stripped of support, the fibers buckle violently under the pressure. They collapse together, forming a steep, concentrated ridge called a kink-band. The bend becomes so extreme that the individual fibers actually snap. They fracture along two distinct planes, instantly turning a solid, rigid rod into a localized, broken hinge. That microscopic hinge cannot hold the weight of an aircraft. Its sudden failure cascades outward, triggering a chain reaction that tears through the rest of the composite material. Fiber kinking is a coordinated cascade of matrix yielding and fiber fracture. It dismantles the structural integrity of the composite in milliseconds. Understanding the physical triggers of kinking is only half the battle. If engineers cannot efficiently predict when and where it will happen, they cannot design around it. This chart shows the complex stress and strain physics of a composite collapsing under pressure. Tracking that highly nonlinear backward slope requires complex mathematical solvers and immense computational power. Using traditional continuum math, simulating a realistic three-dimensional microscopic volume of these fibers requires supercomputers to crunch numbers for weeks at a time. A new computational approach called the Shell-Beam Micromechanical Model changes how software translates the physical material. Instead of calculating dense, three-dimensional solid blocks, this model simplifies the math. It treats the complex 3D matrix as flat, two-dimensional planes called shells and the individual fibers as one-dimensional lines called beams. By stripping away the heavy geometry, engineers can run simulations with the exact same physics and accuracy as the older models, but it operates over 99% faster. By mastering this rapid computational modeling, aerospace engineers can iterate designs in hours instead of months, moving us closer to building aircraft structures that can handle any compressive load without breaking.